Okay, I should be online. Let me just quick check that stream is online and working. And it looks like we're good, so let's once more just get right into it. Chapter 13, the structure of groups. The ultimate goal of group theory is to classify all groups up to isomorphism. That is, given a particular group, we should be able to match it with a known group via an isomorphism. For example, we have already proved that any finite cyclic group of order n is isomorphic to Z sub n. Hence, we know all finite cyclic groups. It is probably not reasonable to expect that we will ever know all groups. However, we will often classify certain types of groups or distinguish between groups in special cases. In this chapter, we will characterize all finite abelian groups. We shall also investigate groups with sequences of subgroups. If a group has a sequence of subgroups, say G with Hn, G is equal to Hn, and then Hn minus 1 is a subgroup of Hn, all the way up to H1 is H0 is a subgroup of H1, and H0 is equal to the identity element, where each subgroup Hi is normal in H of I plus 1, and each of the factor groups AHI plus 1 over Hi is abelian, then we may call, for example, G a solvable group. In addition to allowing us to distinguish between certain classes of groups, solvable groups turn out to be central, and I re-emphasize central, to the study of solutions to polynomial equations. Section 13.1, Finite Abelian Groups. In our investigation of cyclic groups, we found that every group of prime order was isomorphic to Z sub p, where p was a prime number. We also determined that Zmn is isomorphic to Z sub m times Z sub n, when the greatest common divisor of m and n is equal to 1. In fact, much more is true. Every finite abelian group is isomorphic to a direct product of cyclic groups of prime power order. That is, every finite abelian group is isomorphic to a group of the type Z sub p1 to the m1 times Z sub p2 to the m2 all the way up to times Z sub pn to the mn, where each p sub k is prime, which is not necessarily distinct. First, let us examine a slight generalization of finite abelian groups. Suppose that G is a group and let G sub I be a set of elements in G, where I is some index at I, not necessarily finite. So for example, we could have, basically what we'll call this will be our group G, with elements like blah blah blah, like elements so, and we'll have some subgroup, or we'll have some subset, which is the set G sub I. The smallest subgroup of G containing all of the G sub i's is the subgroup of G generated by the G sub i's. So I should also quick note that I don't know if we're going to go over this, but when we say that it is smallest, what we mean is that if, let's call H prime this subgroup, right? Then, if H, the subgroup generated by G sub I, which we're just going to be noting by G sub I, is equal to, or we can call it kind of like, we use cyclic-esque notation, is equal to H prime. So we say that if K is a subgroup of G, and Gi is a subgroup of, or a subset of K, then H prime is a subset of K. So basically, it's the group such that every group, it's the group such that every subgroup that contains that also contains that subgroup. That's the sense in which it's smallest. If this subgroup is in fact all of G, then G is generated by the set G sub I for I and I. In this case, the Gi's are said to be generators of G. If there is a finite set G sub I and I, that generates G, then G is said to be finitely generated. Example 13.1. Obviously, all finite groups are finitely generated. For example, the group S3 is generated by the permutations 1, 2, and 1, 2, 3. The group Z times Z sub n is an infinite group, but is finitely generated by 1, 0, 0, 1. Example 13.2. Not all groups are finitely generated. Consider the rational numbers Q under the operation of addition. Suppose that Q is finitely generated with generators P1 over Q1 all the way to Pn over Qn, where each Pi over Qi is expressed in its lowest terms. Let P be some prime that does not divide any of the denominators Q1 to Qn. We claim that 1 over P cannot be in the subgroup of Q that is generated by P1 over Q1 all the way to Pn over Qn, since P does not divide the denominator of any element in this subgroup. This fact is easy to see since the sum of any two generators is Pi over Qi plus Pj over Qj is equal to Pi Qj plus Pj over Qi and Qj. And since it doesn't divide any of the Qi Qj, well, we obviously can't have a denominator that simplifies down to something over Pi, or over our next P. Proposition 13.3. Let H be the subgroup of G that is generated by Gi in G, where I and I. Then H is an H exactly when it is a product of the form H is equal to Gi1 to the A1, all the way up to Gin to the An, where the Gik's are not necessarily distinct. So for example, we could have some element under this interpretation that like H might be equal to G1 cubed, then we have G7 to like the 1284, another G1, and then G4 to the 17. So note here that we don't have these being necessarily distinct, but we have we restrict ourselves to be a finite amount of them. And we need the case also where these are not necessarily distinct for the non-abelian case, because the non-abelian case complicates things a lot. Proof. Let K be the set of all products of the form Gi1, A1, all the way up to Gin, An, where the Gi's are not necessarily distinct. Certainly, K is a subset of H. We need only show that K is a subgroup of G. If this is the case, then K is equal to H, since H is the smallest subgroup containing all the Gi's. Clearly, the set K is closed under the group operation. Since Gi naught is equal to 1, the identity is in K. It remains to show that the inverse of an element, G equals Gi1, K1 all the way to Gin, Kn, in K must also be in K. However, G to the negative 1, Gi1, K1 all the way to Gin, Kn, is equal to Gi to the negative Kn all the way to G1 to the negative K1, which is in our subgroup, or in our subset that we defined to be for it to be. Note here as well something when you work, like if you work with infinite groups, it is important to note something. We are defining these to be finite products. We don't necessarily have, especially if you don't have a topological structure on this, it doesn't make sense to take this operation out to infinity. For example, just think of how like some infinite additions in the real numbers are convergent, while some infinite additions in the real numbers are divergent. And you need that extra topological structure to talk about that. So we need to add some extra explicit structure to like whatever space you're working on if we want to make sense of infinite products, infinite sums, infinite things like that. Alright, the reason that powers of a fixed Gi may occur several times in the product is that we may have a non-abelian group. However, if the group is abelian, then the Gi's need only occur once. For example, a product such as a to the negative 3, b to the 5th, a to the 7 is an abelian group, could always be simplified, in this case to a to the 4th, b to the 5th. Now, let us restrict our attention to finite abelian groups. We can express any finite abelian group as a finite direct product of cyclic groups. More specifically, letting P be prime, we define a group G to be a P group if every element in G has its order a power of P. For example, both Z sub 2 times Z sub 2 and Z sub 4 are 2 groups, whereas Z sub 27 is a 3 group. We shall prove the fundamental theorem of finite abelian groups, which tells us that every finite group is isomorphic to a direct product of cyclic P groups. So let me just quick write that down. G is a P group if G is in G implies that the order of G is equal to P to the K for K greater than or equal to 0. Fundamental theorem of finite abelian groups. Every finite abelian group G is isomorphic to a direct product of cyclic groups of the form Z sub P1 to the A1 times Z sub P2 to the A2 all the way to times Z sub P2 p sub 2, a to the k. Now, notice here, p and a to the n. Notice here, important thing, we have finite abelian groups here. We're not talking about infinite abelian groups, in which case there's a modified version of this that's stronger, but is not the same. Example 13.5. Suppose that we wish to classify all abelian groups of order 540 equals 2 squared times 3 to the 5th times 5. The fundamental theorem, oh by the way, just to clarify, we're going to be doing the proof later. We're just going to be showing an example now of application. The fundamental theorem of finite abelian groups tells us that we have the following 6 possibilities. z2 times z2 times z3 times z3 times z3 times z5, z2 times z2 times z3 times z9 times z5, z2 times z2 times z to the 27 times 5, z4 times z3 times z3 times z3 times z to the 5, z to the 4th times z to the 3 times z to the 9 times z to the 5, and z to the 4th times z to the 27 times z to the 5. The proof of the fundamental theorem of finite abelian groups depends on several lemmas. Oh, here's the fun stuff, yes. Lemma 13.6. Let G be a finite abelian group of order n. If P is a prime that divides n, then G contains an element of order P. Yes, this is something I love. I love this. Okay, proof. We will prove this lemma by induction. If n is equal to 1, then there is nothing to show. Now, suppose that the lemma is true for all groups of order k, where k is less than n. Furthermore, let P be a prime that divides n. If G contains no proper non-trivial subgroups, then G is equal to the cyclic group A, where A is any element other than the identity. By exercise 4.5.39, the order of G must be prime. Since P divides n, we know that P is equal to n, and G contains P minus 1 elements of order P. Now, suppose that G contains a non-trivial proper subgroup H. Then 1 is less than the order of H is less than n. If P divides H, the order of H, then H contains an element of order P by induction, and the lemma is true. Suppose that P does not divide the order of H. Since G is abelian, it must be the case that H is a normal subgroup of G, and the order of G is equal to the order of H times the order of G over H. Consequently, P must divide G over H. Since the order of G over H is less than G is equal to n, we know that G over H contains an element AH of order P by the inductive hypothesis. Thus, H is equal to AHP is equal to APH, and AP is an H, but A is not an H. If the order of H is equal to R, then P and R are relatively prime, and there exist integers S and T such that SP plus TR is equal to 1. Furthermore, the order of AP must divide R, and A to the P to the R is equal to A to the R to the P is equal to 1. We claim that A to the R has order P. We must show that A to the R is not equal to 1. Suppose in this case that A to the R is equal to 1, then A is equal to A to the SP plus TR is equal to A to the SP plus A to the TR is equal to A to the P S times A to the R T is equal to A to the P S1 is equal to A to the P S. Since A to the P is an H, it must be the case that A is equal to A to the P S is an H, which is a contradiction. Therefore, A to the R is not equal to 1 is an element of order P in G. So, it must be the case that A is equal to A to the PS is, yes, because if this was the case, right, we chose A so that it has order P, so P is the minimum number. However, if this is the case, then we have that A is already an H, it has order 1 instead of order P, which contradicts what we've said previously. Also, this is part of the reason, we've seen a lot of results like this. One of the reasons that I wasn't trying to prove it, it's because factor groups make this an actually, handleable task. Alright, anyways. Lemma 13.6 is a special case of Cauchy's theorem, theorem 15.1, which states that if G is a finite group, and P of prime such that P divides the order of G, then G contains a subgroup of order P. We will prove Cauchy's theorem in chapter 15. Lemma 13.7. A finite abelian group is a P group if and only if its orders is a power of P. Proof. If the order of G is equal to P to the n, then by Lagrange's theorem, then the order of any G in G must divide P to the n, and must therefore be a power of P. Conversely, if G is not a power of P, then it has some other prime divisor Q, so by Lemma 13.6, G is an element of order Q, and thus is not a P group. Lemma 13.8. Let G be a finite abelian group of order n equals P1A1 all the way to PKAK, where is where P1 all the way up to Pk are distinct primes, and A1, A2, all the way up to AK are positive integers. Then G is the internal direct products of subgroups G1, G2, all the way up to Gk, where Gi is a subgroup of G consisting of all elements of order Pi to the R or some integer R. Alright, this is where we're getting to the good stuff. Proof. Since G is an abelian group, we are guaranteed that G sub I is a subgroup for G is equal to I equals 1 all the way to K. Since the identity has order Pi to the 0 is equal to 1, we know that 1 is in G of I. If G is in G of I has order P to the I R, then G to the negative 1 must also have order P to the I, P sub I R. Finally, if H is in G sub I has order Pi to the power of S, then GH to the power of P sub I to the S is equal to G to the P sub I power S, H to the P sub I to the power S equals 1 times 1 equals 1, where T is the maximum of R and S. We must show that G is equal to the internal direct product, and that G sub I is intersected with G sub H is equal to 1 for I is not equal to H. Suppose that G sub 1 is in G1, is in the subgroup generated by G2, G3 all the way to GK. Then G1 is equal to G2, G3 all the way to GK for G sub I and G sub I. Since G sub I has order P to the AI, we know that G to the I, P to the A sub I is equal to 1 for I equals 1, I equals 2, 3 all the way to K. And that G1 to the P2 to the A3 all the way on like that is equal to 1. Since the order of G sub 1 is a power of P sub 1, and GCD of P sub 1, P sub 2 a to the I, P sub, all the way up to P sub K a to the K is equal to 1, it must be the case that G sub 1 is equal to 1, and the intersection of G1 with any of the subgroups G2, G3 all the way up to GK is the identity. A similar argument shows that Gi sub cap Gj is equal to 1 for I not equal to J. This was a lot, and this is very wordy, and I know the first time I read it I was confused. This is actually fairly simple. It's just written in a bunch of cumbersome notation because we have superscripts of superscripts. Basically, we can't have two elements that are coprime. And yet still have one raised to the same order gives us 1. So the only way that's possible is if they're the same thing in the first place, or if one of them is 1 in the first place. Because then they're technically coprime, and they still follow that relation. And the only way for an element to have order 1 is for it to be the identity. That's functionally what this is saying. It's just in a bunch of technical jargon to make sure that everything actually clears out. And this is basically because we can replace G sub 1 in the argument with any other thing. Next, we show that it is possible to write G and G as a product G sub 1 to G sub K, where Gi is in Gi. Since the order of G divides the order of G, we know that the order of G is equal to P1, B1, P2, B2, all the way to PK, BK, for some integers B1 all the way up to BK. Letting AI is equal to the order of G divided by P sub I to the BI. The AIs are relatively prime. Hence, there exist integers B1 all the way up to BK, such that A1, B1 plus on and on plus AK, BK is equal to 1. Consequently, G is equal to G to the A1, B1 plus on and on plus AK, BK equals G1, A1, B1 plus on and on times G to the AK, BK. Since G to the AI, BI, PI to the BI is equal to G to the BI order of G is equal to E, it follows that G to the AI, BI must be in GI. Let GI is equal to AI, BI. Then G is equal to G1 all the way up to GK is in G1, G2 all the way up to GK. Therefore, G is equal to the G1, G is equal to G1, G2 all the way to GK is an internal direct product of subgroups. Whew, I'm gonna personally read that again because that was huge. Okay. So it's possible to write G and G as a product G. Since the order of G divides the order of K, we know the order of G is equal to that for integers B1, letting AI be that. The A is a relative prime, hence there exist integers such that we have this sum here. So, from there, we can write G equals GA1 all the way up to that, which is the product of these. Since each of these have order PI to the BI, it follows that each of these GAI, BI, by how we define the GI, is actually going to be in GI. Basically, we're saying that these have order PI, B to the I, so it needs to be in the set of all elements that have order GI, B to the I. And then letting it just be that, we simply have that. This is a simple relabeling, so we don't have to deal with subscripts, which shows that G is actually G is actually made up of the internal direct product of these things. So G equals G1, G2 all the way to Gk is an internal direct product. It is a lot, but it makes sense upon close reading. I'm just going to leave this on the screen, let it linger for a bit, just in case you want a quick second to look over the entire proof again, because the entire proof is, well, simply put, it's a lot. Also, I'm using this as a moment to fix my Twitch, because my Twitch is having some technical difficulties. So really bask in the kind of laboriousness of the proof, but also the simple fact that, like, we're just abusing the fact of what a P group is. We're just using the fact that it has order P to the Bi. And then we're using that to, like, uniquely classify all the elements. And then using some rearrangements because we have an abelian group in this case. Alright. While you're watching that, Twitch, if you could load faster, that would be extremely well appreciated. Twitch, it would be lovely if you loaded. Twitch, now is not the time. No. Okay, it's working. Alright, so it remains for us to determine the possible structure of each PI group, GI, and lemma 13.8. So we've shown that it's the internal direct product of these groups, right? But now we have to actually show what these group structures are. So, lemma 13.9. Let G be a finite abelian P group, and suppose that G and G has maximal order. Then G is isomorphic to the... Then G is isomorphic to the cyclic group generated by G times H for some subgroup H of G. Proof. By lemma 13.7, we may assume that the order of G is P to the n. We shall induct on n. If n is equal to 1, then G is cyclic of order G and must be generated by G. Suppose now the statement holds of the lemma holds for all integers k with 1 less than or equal to k is less than n, and let G be a maximal order in G. Say the order of G is equal to G of the P to the m. Then A to the P to the m is equal to E for all A and G. Now, choose H and G such that H is not in the cyclic group generated by G, where H has the smallest possible order. Certainly such an H exists. Otherwise G is equal to the cyclic group of G and we are done. Let H be equal to the cyclic group generated by H. We claim that G, the cyclic group of G intersected with the cyclic group generated by H is equal to E. It suffices to show that the order of H is equal to P. Since the order of H to the P is equal to the order of H divided by P, the order of H to the P is smaller than the order of H. It must be in it must be in the cyclic group generated by G by the minimality of H. Yeah, important here to note that we have chosen, in this kind of almost algorithm, we have chosen specifically smallest order, and that has very non-trivial consequences. So, yeah, that is, H to the P is equal to G to the R for some number R. Hence, G to the R to the P to the m minus 1 is equal to H to the P to the m minus 1 equals H to the P m is equal to E. And the order of G to the R must be less than or equal to P to the m minus 1. Therefore, G to the R cannot generate G. Notice that P must occur as a factor of R. Say R is equal to PS, and H to the P is equal to G to the R is equal to G to the PS. Define A to be G to the negative SH. Then A cannot be in the cyclic group generated by G. Otherwise, H would also have to be in G, the cyclic group generated by G. Also, A to the P is equal to G to the negative SP, H to the P is equal to G to the negative R, H to the P is equal to H to the negative P, H to the P is equal to the E. We have now found an element A with order P such that A is not in the cyclic group generated by G. Since H was chosen to have the smallest order of all the elements that are not in G, we have the order of H is equal to P. Now, we will show that the order of GH in the factor group G over H must be the same as the order of G in G. If the order of GH is less than the order of G is equal to P to the m, then H is equal to GH to the P to the m minus 1 is equal to G to the P to the m minus 1 H. Hence, G to the P to the m minus 1 must be in the cyclic group generated by G intersected with H is equal to E, which contradicts the fact that the order of G is P to the m. Therefore, GH must have maximal order in G over H. By the correspondence theorem and our inductive hypothesis, G over H is isomorphic to the cyclic group GH times K over H for some subgroup K of G containing H. Oh man, that's just a whole lot of theorems that's being used right there. We claim that the cyclic group generated by G intersected with K is equal to E. If B is in the cyclic group generated by G intersected with K, then BH is in GH cap K over H is equal to H, and B is in the cyclic group generated by G cap H is in E. It follows that G is equal to the cyclic group generated by G times K, implies that G is isomorphic to the cyclic group generated by G times K. That's a lot. That's a lot as a proof. So let's take stock. So first we use a smallest order argument to claim a smallest order argument to claim that the intersection of these two groups is equal to just the identity. This follows from Lagrange's theorem, and the fact that the intersection of the kind of multiplication of two subgroups of a abelian group is another subgroup of order those two groups times each other if they're disjoint. So that means that since we are choosing it to be 1p away, or g to the m divided by p, the cyclic group of G by the inductive hypothesis, yes, that holds. Oh my gosh, this is a lot. And by smallest argument, we have that A cannot be in the order of G if A does not have like non-trivial. If A does not have a certain relation on the actual ordering of it. And then, so we found an element A with order P such that A is not in G. And since H was chosen to have the smallest order of all the elements that are not in G, we have the order of H is equal to P by like assuming something against that. Alright, so from here, we basically use a bunch of statements involving the correspondence theorem to transfer the problem of finding a subgroup to finding a isomorphism of a certain factor group, which then we can transfer from the domain of factor groups back to the domain of subgroups, since the subgroup of the factor group corresponds to a certain actual subgroup in our regular group. And then using basic properties about just this type of multiplication group and the fact that it's abelian, it quickly implies that G is isomorphic to the cyclic group of G times K. The proof of the fundamental theorem of finite abelian groups follows very quickly from lemma 13.9. Suppose that G is a finite abelian group and let G be an element of maximal order in G. If the cyclic group generated by G is G, then we are done. Otherwise, G is isomorphic to Z sub the order of G times H, or some subgroup H contained in G by the lemma. Since the order of H is less than the order of G, we can apply mathematical induction. We now and also note that mathematical induction only gives us the finite case, which is why we have to assume like finitely generated, a finite abelian group. We can now state the more general theorem for all finitely generated group. The proof of this theorem can be found in any of the references at the end of the chapter, which is just like a simple extension of what we've done. The fundamental theorem of finitely generated abelian groups is as follows. Every finitely generated abelian group G is isomorphic to a direct product of cyclic groups of the form Z sub P1 to the A1 times Z sub P2 to the A2, all the way to times Z sub PK to the AK, times a certain finite number of Z's multiplied with each other, where the PI's are primes, which are not necessarily distinct. Whew, okay. Let's chill from the group theory with some more intense group theory, shall we? 13.2. Solvable groups. A subnormal series of a group G is a finite sequence of subgroups, G which equals Hn, which is a subset of Hn minus 1, which is a superset of Hn minus 1, which is a superset on none, which is a superset of H1, which is a superset of H naught, which is equal to the identity, where Hi is a normal subgroup of Hi plus 1. I'm going to note this condition here because this condition is going to be kind of important. So Hi is a subgroup of H1 subset of H naught is equal to the identity, where Hi is a subgroup of Hi plus 1. If each subgroup Hi is normal in G, then the series is called a normal series. The length of a subnormal or normal series is the number of proper inclusions. So example 13.11. Any series of subgroups of an abelian group is a normal series. Consider the following series of groups. So we have Z as a superset of 9Z, as a superset of 45Z, as a superset of 180Z, as a subset of 0. And C sub 24 as a subset of the group generated by 2, as a subset of the group generated by 6, as a subset of the group generated by 12, as a subset of 0. Example 13.12. A subnormal series need not be a normal series. Consider the following subnormal series of the group D4. So D4 is a superset of 1, 1, 2, 3, 4, 1, 3, 2, 4, 1, 4, 2, 3, is a superset of 1, 1, 2, 3, 4, is a superset of 1. The subgroup 1, 1, 2, 3, 4 is not normal in D4. Consequently, this series is not a normal series. A subnormal or normal series is called a refinement of the subnormal or normal series H sub I if every single H sub I is a subset of K sub j. That is, each H sub I is one of the K sub j. So we have this series. I'm going to go in reverse order from what the text says. So first of all, assume we have some like Z as a superset of 9Z, superset of 45Z, superset of 180Z, superset of 0. Then we have a refinement, Z, superset of 3Z, superset of 9Z, superset of 45Z, superset of 90Z, superset of 180Z. Notice that when we refine, we still have Z, 9Z, 45, 180, Z, and 0, all in, like they're all going to be in the series. It's just we've added more terms. The best way to study a subnormal or normal series of subgroups H sub I of G is actually to study the factor groups H sub I plus 1 over H sub I. We say that two subnormal or normal series H sub I and K sub j of a group are isomorphic if there is a one-to-one correspondence between the collections of factor groups Hi plus 1 over Hi and Kj plus 1 over Kj. Yeah, so it's about the length in this case. Example 13.14. The two normal series Z sub 60, superset of 3, superset of 15, superset of 0, and Z sub 60 is a superset of 4 as a superset of 20 as a superset of 0. Of the group Z60 are isomorphic since Z sub 60 over 3 is isomorphic to 20 over 0 is isomorphic to Z sub 3. 3 over 15 is isomorphic to 4 over 20 is isomorphic to Z over 5. And 15 over 0 is isomorphic to Z60 over 4 is isomorphic to Z sub 4. Oh gosh. A subnormal series H sub I of a group G is a composition series if all the factor groups are simple. Note here that simple implies no non-trivial normal subgroups. A normal series H sub I of G is a principal series if all the factor groups are simple. Example 13.15. The group Z sub 60 has a composition series Z sub 60 as a subset of generated by 3, subset generated by 15, subset generated by 30, subset of 0, with factor groups Z sub 60 over 3 is isomorphic to Z mod 3, 3 over 15 is isomorphic to Z mod 5, 15 over 30 is isomorphic to Z mod 2, and 30 over 0 is isomorphic to Z sub 2. Since Z sub 60 is an abelian group, the series is automatically a principal series. Notice that a composition series need not be unique. The series Z sub 60, as a subset of 2, subset of 4, subset of 20, subset of 0, is also a composition series. Example 13.16. This is going to be a very prominent example, but you won't understand why for a while, but just know it's extraordinarily useful. For n greater than or equal to 5, the series S sub n, followed by A sub n, followed by 1, is a composition series for S sub n. Since S sub n over A sub n is isomorphic to Z mod 2, and A sub n is simple. Let me also double check something. If the factor groups are simple, and it's principal, yeah. Wait, if all the factor groups are simple, a normal series. If all factor groups are simple, why are they called two different things? I feel like, is this a mistake in the textbook? A subnormal series H sub I of a group G is a composition series. Oh, so it's the difference between a normal and a subnormal. If it's subnormal, it's composition. If it's a normal, it's a principal. Okay. Example 13.17. Not every group has a composition or a principal series. Suppose that 0 is equal to h0 is a subset of h1 is subset of all the way to hn minus 1, subset of hn is equal to z. Is a subnormal series for the integers under addition. Then h sub 1 must be of the form kz for some k and n. In this case, h1 over h0 is isomorphic to k sub z is an infinite cyclic group with many non-trivial proper normal series. Although composition need not be unique as in the case of z sub 60, it turns out that any two composition series are related. The factor groups of the two composition series of z sub 60 are z sub 2, z sub 2, z sub 3, and z sub 5. That is, the two composition series are isomorphic. The Jordan-Holder theorem says this is always the case. Oh, let's go. This is going to be quite the proof. So suppose now, actually wait, now let me actually read the whole statement. Jordan-Holder, any two composition series of G are isomorphic. Proof. We shall employ mathematical induction on the length of the composition series. If the length of a composition series is 1, then G must be a simple group. In this case, any two composition series are isomorphic. Suppose now that the theorem is true for all groups having a composition series of length k, where 1 is less than or equal to k is less than n. Let G is equal to hn is a superset of hn minus 1, all the way to h1 is a superset of h0, and G is equal to km, greater than or equal to km minus 1, is a superset of k1 all the way up to k0, be two composition series for G. We can form two subnormal series for G, since h sub I cap k sub m minus 1 is normal and h sub I plus 1 cap k sub m minus 1, and k sub j cap hn minus 1 is normal and k sub j plus 1 cap hn minus 1. So this is a relation between the two series. So we have that G is, in our first new series, is going to be equal to h as a superset of hn minus 1. It's a superset of hn minus 1 cap km minus 1, all the way to superset h0 cap km minus 1 is equal to the identity. And we have G is equal to km as a superset of km minus 1, as a superset of km minus 1 cap hn minus 1, all the way up to cap k0 intersected with hn minus 1. Since hi cap km minus 1 is normal and hi plus 1 cap km minus 1, the second isomorphism theorem, or theorem 11.12, implies that hi plus 1 cap km minus 1 over hi cap km minus 1 is equal to hi plus 1 cap km minus 1 is equal to hi cap hi plus 1 cap km minus 1 is isomorphic to h sub I, hi plus 1 cap km minus 1 over h sub I, where hi is normal in h sub I, hi plus 1 cap km minus 1. Since h sub I is a composition series, hi plus 1 over hi must be simple. Consequently, hi plus 1 cap km minus 1 over hi is either hi plus 1 over hi or hi over hi. That is, hi plus 1 cap km minus 1 must be either hi or hi plus 1. Removing any non-proper trivial inclusions from the series hn minus 1 hn minus 1 superset hn minus 1 cap km minus 1 cap on and on cap h0 cap km minus 1 is equal to e, we have a composition series for hn minus 1. Our inductive hypothesis says this series must be equivalent to the composition series hn minus 1 cap on and on cap h1 cap h0 is equal to e. Hence, the composition series G is equal to hn cap hn minus 1 cap on and on cap h1 cap h0 is equal to e, and G is equal to hn cap hn minus 1 cap hn minus 1 cap km minus 1 cap on and on cap h0 cap m minus 1 equals e are equivalent. If hn minus 1 equals km minus 1, then the composition series hi and kj are equivalent and we are done. Otherwise, km minus 1 is a normal subgroup of G properly containing hn minus 1. In this case, hn km minus 1 is equal to g, and we can once again apply the second isomorphism theorem. That is, k to the n minus 1 over k to the n minus 1 cap h to the n minus 1 is isomorphic to h to the n minus 1 k to the n minus 1 over h to the n minus 1 minus g over h to the n minus 1. This is just for a simple restriction of domain. Therefore, g is equal to h sub n as a supersets hn minus 1, superset on non to h naught. Excuse me then. Superset of h naught cap k to the m minus 1 is equal to e, and g is equal to k to the m, superset k to the m minus 1, cap k to the m minus 1, cap h to the n minus 1, on non up to k naught cap k to the n minus 1 is equal to e, are equivalent, and the proof of the theorem is complete. Whew boy, that was definitely a theorem. So, I'm going to quick read through this proof again personally. So, we have these two series, these two composition series. We can form two subnormal series since we have, because it's a composition series, subnormal series if all the factor groups are simple. So we have the factor groups are able to be defined, so we know that all these groups are normal. And so hi is normal, and then because these are domains that contain it, this is obviously true. And then this is obviously true because of that. So we can form these subnormal, these two subnormal, not necessarily like nice series, but these two subnormal series. So the second isomorphism theorem tells us more uniquely what the factor groups of these are. So this is like descending by one, which we can just then apply the definition, and we can get an isomorphism using the second isomorphism theorem here. Hi plus 1 cap km minus 1 where hi is normal and hi plus 1 cap km minus 1. Since hi is a composition series, hi will be simple. Yes. Consequently, hi plus 1 cap k minus 1, since this is a normal group, this is going to be a normal subgroup by like the fact that we're working with normal subgroups. We either have it's going to be the identity, or it's going to be the only non-trivial subgroup. That is hi plus cos, removing a number of exclusions. Then it gives us a composition supposed to be equivalent to that. This composition series are basically applying the inductive hypothesis along with everything here changes our series to be these two equivalent series. It must be equivalent if hn minus 1 equals km minus 1 from here, because this would be equivalent here, and this sets us up to success. We are done. Because we've now replaced all cases of k in this with h, which is a very powerful thing that we've done with the previous isomorphism theorem. That's like the first case. Otherwise, k to the n minus 1, k to the n minus 1 is a normal subgroup of G properly containing hn minus 1. In this case, hn minus 1, kn minus 1, and we can apply the second isomorphism theorem to get this kn, which gives us identity here, which gives us that these two equivalent series. Yeah, which gives us these two equivalent series here, and we're using a similar logic. Since they're equivalent, the proof of the theorem is complete, which shows that, because the two series are equivalent. Yeah, perfect, okay. That is starting to make sense now. I might need another pass this in my personal time, but I'll do that off stream, because this is just very much hardcore, know the definition. Especially reviewing that second isomorphism theorem. A group G is solvable if it has a subnormal series hi, such that all the factor groups hi plus 1 over hi are abelian. Just going to say, the word solvable should be a big hint that those are really important. Solvable groups will play a fundamental role when we study Galois theory and the solution of study of polynomials. Alright, here is the big thing that we're going to build up to real quick. The group S4 is solvable, since S4, subset of A4, is a subset of 1, 1, 2, 3, 4, 1, 3, 2, 4, 1, 4, 2, 3, subset of 1, has abelian factor groups. However, for n greater than or equal to 5, the series Sn subset An subset of 1 is a composition series for Sn with a non-abelian factor group. Therefore, Sn is not solvable for groups, is not a solvable group for n greater than or equal to 5. Which also is the one of the things it had mentioned for the alternating group to specifically be non-abelian, and a lot of reasons we did the work with the alternating group so intensely. Alright, Sage, nobody cares. Okay. How many abelian groups are there of order 200, 2 to the 3, 2 to the 5 squared? So let's just like literally write all these out. So 2 to the 3. Okay, 2 to the 3, 2 to the 5, 2 to the 3, 5 squared. 3, 5 squared. So we have z2 times z2 times z2 times z5 times z5. We can collapse two of them to get z4 times z2 times z5 times z5, z4 times z2 times z25, z4, actually no, z8 times z2 times z5. Oh wait, no, I didn't have a times 2 there. z5 times z5, z sub 8 times z sub 25, 25. And we as well have the cases where we multiply this. We have two cases, one for where it's 5 and 5, and one for it's 25. And for this I actually counted everything else. So 1, 2, 3, 4, 5, 6. So we have 6 total groups, which corresponds to the product of those is equal to 6. How many abelian groups are there of order? 729 equals 3 to the 6. So there'll actually be, I'm pretty sure there'll be 6, yeah, there'll be 6 groups. It's saying if abelian groups, yes. So we have this, 3, 1, 2, 3. And then we just have, like, we collapse it, and we're able to collapse it like 5 more times until we get z sub 3 times 3 to the 6, which shows that there are 6 possible groups. Find a subgroup of order 6 in z sub 8, z sub 3 times z sub 3. So we need to simplify it in an element. So yeah, find a subgroup of order 6. So we need 4, 1, 0. If we raise it to the third, or no, we raise it to the 6, 6 will be the minimum number, such that it's 0, 0, 0. It can be shown that an infinite abelian group of order 27, 72 contains a group of order 8, What are all possibilities for this subgroup? So it's an abelian group of order 72. So it's either, yeah, it's some combination of z8, z4 times z2, or z2 times z2 times z2. It's one of those three because it's a abelian group, and it finally generates itself. What is a principal series of a group G? Your answer should not use new terms in this defined in this chapter. That's weird when you're literally asking to define a principal series. But a principal series is basically a decreasing chain of normal groups, with each factor group being, I forget if the principal series, the principal series at each is not, yeah, if all factor groups are simple. Alright, that was a lot. I'm expecting these exercises to kind of mess me up after all that. Oh god, and looking at these are not fun either, so we'll see. Shh. Alright, so yeah, I guess before I do that though, my standard intermission. Okay, I'm back. Pretzels were pretty good. Twitch does not seem to be as good though, as my pretzels were. Give me a second to reload stream, make sure things are working, and we will begin work on these problems. I may not get to some of the harder results at the end. Because also, it's been a while. I streamed a lot of math today. And as such, I'm quite tired, so I'll try to keep it like a healthy level of math. We'll see how things pan out though. I honestly might just do math until like 3 a.m. or something like that. Like I've done it before, I'll do it again. Alright, stream seems to be working, it looks like. Yeah, okay. Stream seems to be working, just kind of a bit behind, so get rid of that. Eating pretzels, because I'm done eating pretzels. Alright, find all abelian groups of order less than or equal to 40 up to isomorphism. So it's just going to simply be for this. I don't want to like write all this down, because for all the abelian groups, it's just fundamental theorem of finite abelian groups, or finitely generated abelian groups, and it's just taking that prime factorization, of it, and then doing that. So for the sake of just stuff, okay. Find all of the composition series for each of the following groups. So Z mod 12. Z mod 12. First of all, we know the subgroup generated by 2, subgroup generated by 4, subgroup generated by 6. I know. Actually, not necessarily. Actually, wait, no, yeah, it is. Okay. So let's show that this is simple. So Z mod 12. Actually, let me write it. Z mod 12 over 2. Well, we know that this factor group is going to have order 2, which means that it needs to be isomorphic to Z mod 2. Right? So then we have order of 2 over order of 4 is going to once again be isomorphic to Z mod 2. Because it will just determine whether or not your thing is a multiple of 2. Is 1 time a multiple of 2 or 2 times a multiple of 2. If it's 2 times a multiple of 2, then it's in 4. If it's 1 times a multiple of 2, then it's in 2. And then we have the cyclic group generated by 4 has order, since we're working Z mod 12, 3, which means that this is isomorphic to Z mod 3. So we could also say that we can write Z mod 12 as the subnormal series Z mod 2, Z mod 2, Z mod 3. At least when we think of the factor groups. And this does, yes, in case you're wondering, this does have to do with the specific prime factorization of 12. But that's something I don't know if I'm going to prove now. Let's see, actually, Z48, the quaternion has D8. Oh gosh. I'm just not going to worry about all this for now, because I don't like computations. I'm way too tired for late night computations. So we're going to just assume that 4 has been solved for us. So show that the infinite product G equals Z2, Z2 all the way is not finitely generated. If it was finitely generated, we just take that sum. So there'll be some, alright, basically, how do I best describe this? So we want to show that Z2 times Z2 times, it's not finitely generated. It's not finitely generated. So what this would mean is, suppose it was finitely generated. Then we would have G1, G2, all the way up to G sub k. Generate it. However, note that every element is of the form G1, because it's finite, because it's abelian. It would be G1 to the k, k1, G2 to the k2, all the way up to G to the k, k. That's, you know what, let me change that. I just realized I should think harder before I use my notation. Yeah, here we go. P1, P2, G to the k, pk. Now, how many possible elements are there of this form? Notice that since every group has order 2, we have P1, P2, all the way up to pk equals plus or minus 2, which is definitely the amount of total elements of this form. So the order of the group generated by elements of this form is less than or equal to the k. Actually, I think it's equal, but it's less than or equal to 2 to k, but it's strictly less than infinity. However, this group has infinite order, while the subgroup generated by it has finite order. Therefore, we can't have a group with finite order generate a group of infinite order, because literally the orders do not even match. Alright. And this actually works for any product of a finitely generated product of cyclic stuff. As long as the cyclic stuff is kind of bounded, in the sense that we can choose a maximum that k must be. Because if it's not bounded, then it actually might, but in this case, we can. So let G be an abelian group of order m. If n divides m, prove that G has a subgroup of order n. Alright. Let G be an abelian group of order m. If n divides m, prove that G has a subgroup of order n. We basically apply it to the prime factorization to get elements in the prime factorization. So if n equals p1, let me choose better notation, let me think ahead, q1, p2, q2, all the way up to pk, qk, then, well, for each, we've already proved that it has a group of this order, right? So we have orders, we can consider them G1, or we have elements Gi such that, or subgroups H, such that the order of H is equal to Gi. Or actually, no, we show that it's a P group, so we actually show that there are elements Gi such that the order of Gi is equal to P to the 1 A1. So then we just take the internal product of all those, and we get a group with order n. So it's not really an application of n, more so the prime factorization of the p group stuff of m, of k. A subgroup G is a torsion group if every element of G has finite order. Prove that a finitely generated abelian torsion group must be finite. So for this, roughly what you're going to be doing is you're going to be so we can basically put an upper bound on the size of the torsion group. So let G be such that every G I is in a GI. The order of GI is less than infinity. Now let G1 up to Gn generate G. Now what this means is that because the group is generated by this, we have finite generation here, and it's abelian, every element is equal to G1, G2, all the way to Gn for A1, A2, all the way up to AK. Now, how many of the possible elements of this form are there? Well, we know that we have 0 is less than or equal to A1 is less than or equal to the order of G1, right? Because if we go over, we're just going to loop back around. And likewise, we're going to have ultimately 0 is less than or equal to A sub I is less than or equal to G sub I. However, if there are only like these many possible combinations, we have at most, we can put an upper bound on G as being less than or equal to we'll write it as this, the product of the order of GI, which is strictly less than infinity, because each element has finite order, and we are having a finitely generated group. Which means that, bada boom bada bing, we get that our torsion group is finite. At least if it's abelian. If it's not abelian, we get more subtleties. Let GH and K be a finitely generated abelian group. Show that if G times H is isomorphic to G times K, H is isomorphic to K. Give an example, a counterexample to show this cannot be true in general. So what it's going to come down to is that since it's finitely generated, we can show that the products form a finite generation set for these, which allows us to put a one-to-one correspondence, and as such an isomorphism. And the counterexample to show that it's not true in general is that if our groups are non-finitely generated abelian, we can use the classic example Z times on and on. An infinite product. Let G and H be solvable groups. Show that G times H is also solvable. And I don't want to work with composition series tonight. I'm way too tired. Let me see if there's anything good here. Because, like, I want to do this. But at the same time, God, no. Alright. So we're not going to worry about composition or principal series stuff tonight. This is my executive order now. Because I'm very lazy. And be an also group of G if I don't know if G is a solvable group. But if the G is a solvable group, if and only if G is a series of subgroups with Pi is 1. And the order of Pi plus 1 is prime. Yeah. I mean, the thing is, if the order of this is prime, well, it's going to need to be prime, because if it's not, if there's a prime that divides it, there's an element of that order. Take the cyclic group of that, we have a non-normal series. And then what does it require that G be solvable? If all factor groups are abelian. And if it's, if the factor groups are prime, right? If the factor groups are prime, then we have that. Let me think of what I'm saying. Yeah, if the factor groups are prime, then we have that the group is necessarily abelian. And the only way for it to be both abelian and simple, the only way for it to be abelian and simple is if we have the cyclic groups of prime order. So that's the only way we can have a solvable group. That should be a solvable group. It's good enough. And a simple subgroup of G prove that G over N is solvable. The unsolvable geez, composition series. Oh gosh. I'm just like not even gonna worry about this. Jesus, trivial abelian subgroup. This is like a possibly really cool exercise, but I'm not gonna worry about that right now because basically the solvability gives you a nice factor group. You use the one-to-one correspondence or the like factor correspondence thing, I forget what it's specifically called, to show that hey, we have a non-trivial like subgroup, and then subgroups with this certain thing end up being abelian. Alright, the commutator subgroup would find a series of groups G naught G1 equals G prime, Gi prime equals Gi prime. Series called the derived series of G. Only if G is to the n is equal to E for some integer E. So show that you can know a non-trivial abelian factor group. Yeah, okay. I'm way too tired to do most of this. I think I might just end it here. We got good work done with the admittedly little that we did do. And we went and read through some very hard material. But a lot of this is just somewhere where I'm not kind of in it right now to do math to the level that I need to for this. Especially because, like, the solvable stuff is really simple, like, ultimately. But I'm way too tired to get it. And I don't want to be pushing myself to where I'm starting to get bad habits when I do math. So, out of the sake of worry for myself, I'm just gonna stop for now and take it as easy as I can. So, in that case, see ya. Oh no, not see ya. Oh gosh. Thanks for tuning in. Have a nice